Today we are very happy to invite Lin Ting-Chun to come to give us a talk about the error coding. Ting-Chun David, he graduated, his undergraduate is at MIT, and last year he came back to Taiwan for working for some a project in HonHai for some period. Now he is a first year graduate student at UCSD, so let's welcome him.
Okay, hello. Yeah, okay, yeah, thanks for the introduction. And yeah, so this is a new result based on a joint work with Michelle Xie at HonHai. Yeah, so yeah, and today we're talking about good quantum LDPC code. Yeah, so let's start with the goal. So, okay, can people see the goal? Okay, yeah. So the goal is that we want to find a quantum LDPC code. Okay, we want to find a quantum LDPC code with linear distance and constant rate. Okay, so we see a lot of new vocabularies. So we will go through them. So first, we'll focus on the quantum. So what's a quantum code? Yeah. So in the classical case, there are linear codes and nonlinear codes. And for quantum, we have stabilizer codes and non-stabilizer code. But in the quantum case, the stabilizer code are always easier to define. So for our purpose now, we will just focus on the stabilizer code. All right, so every time we want to talk about code, we have to tell you what's a code space. So in this case, the code space is a Hilbert space, and these are the code words. So your code words lives on n qubits. So these are qubits, and you have n copies of them. And what these code words has to satisfy is that after applying S, you return the same state. So what are these S? These S are polystrings of length n. So equivalently, that means on each qubits, you have, it's either like identity or X or Y or Z. So note that these polystrings has a nice property, which is that when you take a square, it's 1. So that means its eigenvalue is either +1 or -1. And so this is pretty similar to parity check in the classical situation. So the parity check in the classical situation is saying that the bits, when you add up some bits in your code word, it has to sum up to 0. And here we are saying that if you apply some poly operators on some qubits, then it has to end up with with eigenvalue 1. So the similarity is here. So stabilizers correspond to the parity check in the classical situation. So in the classical situation, the parity check could be anything. But in the quantum case, these stabilizers have to satisfy some property. And the property is this commuting property. So that is, for any S and T you picked in your stabilizer set, they have to commute. And so why is that? The reason is that if they don't commute, then you actually would end up with an empty code space. And so, yeah, that's where this requirement comes in. Okay, so that's for the quantum code. But in fact, we will look at an even specialized version, which is this quantum CSS code. So quantum CSS code is a stabilizer code with additional property, which is all their stabilizers are either X stabilizer or Z stabilizer. That means all the poly operators in the stabilizer is all of them are X or all of them are Z. So what's nice about this is that now we can group those X stabilizers together and then the Z stabilizers together. So these are similar to the parity check matrix in the classical situation. And now the commutator property naturally, okay, the commutator property becomes this equation, this relation between the two matrices. Okay, so that's a lot of equations, so let's look at an example. So we'll use this short code as our example. So the short code is a CSS code, because we could see that. Okay, so let's first look at what this picture means. So here we have 9 qubits. So these are the qubits. So there are 9 of them. And then there are 8 stabilizers. So the first 8 contains only Z, so that's the Z stabilizer. The last 2 contains only X, so those are the X stabilizer. And now we can group them into matrices. So we can write X as 1 over here, and then 0 as like an identity as 0 over here. So that's how you construct your HX. Similarly, you can construct your HC. And so you can check this condition, HX times HC transpose. And you'll see that it's 0. So let's just do one example. So let's take the first row and the first row for HC. And we can compute their overlap. So when we look at their overlap, they overlap on the first 2 qubits. So yeah, and just to remind everyone, like the field that we are working in is in F2, and so 1 + 1 = 0. Yeah, are there some questions? Yeah, if you have any questions, you can just unmute yourself.
What's the meaning you are talking about of the overlap? What's the effect?
Okay, so what I'm doing is, yeah, so okay, so this is my HX, right? And then for my HZ, I would have 1 1 0 0 0 0 0 0 1 1 0 0 0 0 0. And so what I'm computing was, okay, when you multiply the 2, you will end up with a matrix of size 2 times 6. Okay, so I'm computing this entry. So I'm showing that this entry is 0 by taking the inner product of these 2 vectors.
Okay. And then the 0, then what's the next for the matrix entry to be 0?
Can you repeat again?
I mean, yeah, if you
why
have...
it has to be 0?
No, I know it's 0. So what, when the matrix 0 has 0 entry or 1 entry, what will it affect the next step?
So when, okay, so the reason that we need hx.hc transpose to be equal to 0 is because that's required for the code to be a well-defined code. That means the stabilizer has to commute.
Okay, I see. Thank you.
And the reason is that so X and Z, they anti-commute. So yeah, so that means for 2 stabilizers, they always have to, the X stabilizer and the Z stabilizer, they always have to overlap on an even number of sites. So for example, XX and ZZ, they would commute because they overlap on an even number of sites. So more precisely, I can write it this way. So X1 is the X operator acting on the first qubit. Z1 is the Z operator acting on the first qubit. And so you see that they need to have an even overlap of number of qubits to make them commute.
So this is a sequential operation and the qubit.
Yeah, at the same time they commute, and so the order doesn't matter.
Okay,
so you're saying, yeah. So because they act on a different site, and so they commute. And so, yeah. And the reason that people like CSS code is because you can actually think it in another language, which is the chain complex. So this is chain complex is some object in math which contains 3 vector space and 2 linear map. And moreover, when you compose a linear map, it has to be 0. So that's the requirement for a chain complex. And turns out the requirement that when you go through the 2 arrow, it has to be 0. This condition is exactly the same as the condition of the stabilizer code. So it makes it really appealing. And so just to say a few more words. So this VZ in this case, it's a F2 vector space generated by the Z stabilizers. Since there are 6 Z stabilizers, it's same as F2 6. And for X stabilizers, it's F2 2 because there are 2 stabilizers. And for the V qubits, there are 9 qubits. So overall, it looks something like that. So that's the chain complex. And later on, because to simplify the notation, we'll use like V-1, V0, and V1. And then there are some partial signs in between. So they stand for the H. So that's just a notation change. And that will only appear once. And I'll remind everyone about that. So just to know that it will appear later. Okay, so that's the quantum code. So for quantum code, just we need to specify HX and HZ. And they had to satisfy the property, mutation property. Okay, so next we'll talk about distance and rate. And the rate is easier to explain, so we'll begin with that. So for every code, Bo would attach it with some parameters. So n, k, and d, and we'll go through them. So n is the number of physical qubits, which we have seen before. So that is this, f2 to the nth power. And k is the dimension of the code space. So equivalently, it's saying, okay, how many qubits can I encode using this error correcting code? And so the rate is the ratio between the two. So a constant rate here would mean that k is linear to n. So they are the same thing. So that's for rate. And next we'll talk about distance. So distance is more complicated. So we will first give two definitions. So the first is logical operators. So we'll first give the definition and I'll talk about the physical meaning of it. So the logical operators are the polystrings that commute with the stabilizers. So O, the S inside big S, it has to commute with them. So why do we have this definition? The reason is that for logical operators, you can think it as some operator that transform code word into code word. So it's some operator from code word to code word. And we know that the code word is stabilized by your stabilizer. So S psi is equal to psi. And so, yeah, let's call the logical operator O. So when you apply the operator, when you apply your operator to your state, you want it to still live inside the code word. So that means it should also satisfy this condition since it's inside the code word. And so now you would see that, okay, so now we have these two equations. We can put an O in the front. And we'll see that OS is equal to SO. So similar to the previous argument, this would imply that SNO commutes. Yeah, so
Sorry,
that's why we
or
have.
is the arbitrary operator, or is the special operator you want?
O is some operator that maps the code space into the code space.
So it's by design, you need. Okay.
Yeah, we want to look at these operators. Yeah, because eventually when we're doing quantum computing, then this would be the operator that we act on.
So the goal is to find the operator?
Here I'm just defining a set. And the reason that it's called a logical operator is because, yeah.
I see.
Yeah. Okay, so that's a logical operator. And next we have this trivial logical operator. So the trivial logical operators are the strings that are generated by your stabilizers. And the reason they're called trivial is because stabilizer, when you X on the state, it's the same state. So and because the trivial logical operator are some combinations of these stabilizers, so it's a multiplication of multiple of them. And so you will see that it still doesn't do anything to your code word. So it's the identity.
I have a question. Like initially we have like n qubit physical qubits, and then
yes,
we encode to k qubit, like the logical qubits. And so like I just like, but it's still like this, each of these k qubits like is some particular state of this. Say if I have n equal to 8, so this one of these encoded qubits is actually 8 qubit, then 9. So I mean, then like how to know which is the 0 state or 1 state? Does that make sense?
Do you mean that how do I know which qubit I have in the encoded space? So like yeah, since in the encoded space we also have the notion of qubits. So so is that what you're referring to, the 0 state and the 1 state? Yeah, so the logical 0 and logical 1.
Yes. But I mean like like this, like the logical 0 state, but say if I like if k is equal to 3, then like 3 is like the combination of a physical qubits. Then how do I know it is in the logical 0 state or is in the logical 1 state?
Sorry, I don't understand. Yeah, I didn't understand.
Do you mean in the operation, how do you distinguish the physical qubit and logical qubit in the operation? Do you mean that?
So I mean, it's after encoded is a logical qubit, but just it isn't obvious to me. Like, then how do I know it's logic 0 or logical 1? Then, so now my imagination is I have n qubit, like I have a qubits, physical qubits, and I pick some like some set of stabilizer S. Then say the only states satisfies the stabilized S, like S at S acting on K side equal to psi. The states satisfy this only have 4, like K equal to 4. So then I have this these 4 states. Then, but isn't these 4 states are just like 4 particular states? Then how do I say is logical or is is logical 1 or this is logical 0.
Okay, so how do I distinguish different states and
Yes.
the encoded Hilbert space? So
Yeah.
one way is that, so okay, we can think it in the usual case. So say you have qubits, just a qubit. Then how do you distinguish 0 and 1? So one way is that you can measure like using the Z operator. Using the Z operator, you measure it and you will see that it's spin up or spin down. Right. So it's the same thing. So one way you can do is that you can, say I want to apply Z on two sites. Then the way I can measure it is I can do, I have to remind myself. You can do some control Z and then do another control Z. Let's see if that will work. Yeah, okay, I think, it'll take some time to verify this, but the idea is that you can do some kind of control gates, and then now you can do a usual measurement on this ancilla qubits, and then you can read out the result. So in your case, that would be that, so this is your physical qubits, then there will be some kind of control gates acting on your, so you'll start with some ancilla 0, and then you do some control measurements, and then later you measure this ancilla, see if it's 0 or 1. Then now you can distinguish the logical states.
But you need to design some gate acting on function like
true.
on 1 qubit.
Yes.
Okay.
True. Yeah. Okay. So, all right. So I was talking about this logical operator and trivial logical operator. So now once we have these two, we are ready to define distance. So distance would be the length of the shortest non-logical operator, shortest non-trivial logical operator. So the reason that we need this non-trivial is because in later settings, we will see that the stabilizers are all really short. So stabilizers are only acts on like 4 qubits or 6 qubits, for example. And so, we have to remove them. And so that's why we have this non-trivial inside here. Right, so that's for, and for the goal, we want the distance to be really large, which is linear to the number of qubits. Okay, so that's distance and rate. And the last thing we'll need to talk about is this low density parity check. So what does low density parity check means? So it means that your stabilizer only acts on constantly many qubits. Yeah, so, okay, oops. Yeah, and so and HC, in the previous example, we see that HC is a stack of many stabilizers. And so equivalently, it's saying that, in each row, there are only constantly many ones. Constant number of 1 on each row. So roughly, it's saying that they're sparse. Okay, so now we have everything. And that's our goal. Okay, yeah, this is the goal. Okay, and now I would come back a little and talk about what's the history and some of the motivation. And so there are several different motivations on why people want to study these quantum LDPC code. And the first one is that itself it's already a pretty nice problem. So let me give an example. So here we have the classical error correcting code and the quantum error correcting code. So in the simplest example, in the classical case is the repetition code. So that is you encode 1, 0 into 0, 0, 0, and you encode 1 to 1, 1, 1. For the quantum case, it wasn't so easy. It was until like Shor who found this 9-qubit code. So after this simplest example, now you would want to ask, okay, can I achieve really large distance and have a constant rate? In the classical case, Shannon, that's his like famous paper, which is that you can pick a random code book. So you just randomly pick your code word, and it would be such an example. For the quantum case, it's slightly harder because random code book, this kind of notion doesn't really make sense because there is this commutation relation that has to satisfy. And so CSS, so these are 3 people, they exactly did what we did, which is they focus on these hx hz equals 0. They look at this particular case, and they were able to use some classical construction to make it work. So they basically the CSS construction allows people to translate classical codes into quantum codes. Yeah, and there are many other generalizations of task one can consider, and one of them is to achieve really fast decoding. So previously, I just only care to have large distance and large number of encoded qubits, but I didn't say anything about the decoding time. So oftentimes we want it to be as fast as possible, and linear is the best. And so the next task one can think about is, could there exist a classical code that has linear distance, constant rate, but also has linear time decoding? And that was the motivation for them to develop these LDPC codes. And yeah, and they have linear time decoding. So a natural question to ask is, okay, can we generalize into the quantum setting? So can we have a quantum LDPC code? And if they exist, they probably also have these linear time decoding, which is pretty nice. So that's a pure motivation from the classical, like trying to find the analog in the classical case. But there are also other motivations. So one of them is it could be used in multiple places. And one of them is fault-tolerant quantum computing. So to build a quantum computer, to show that you can like really build a quantum computer that doesn't that has like reliable results, you need to deal with this the problem of error. And to formally define it, it means that you want to make sure, even in the decoding step, you want, in the decoding step, you won't build up too many errors. And what Daniel Gottesman was able to show is that once you have this quantum LDPC code, you can build fault-tolerant computing with constant overhead. Another motivation is in classical complexity theory, there's these PCP theorems, so probabilistic checkable proofs. In those cases, they're related to codes, and especially those local testable codes. So in the quantum setting, these quantum LDPC code may also be related, and so studying these quantum LDPC code could also help us to understand better on these complex quantum complexity problems. Okay, and finally, I just want to talk a little bit about the history. So in the past, people have thought about these codes, and at first, people was able to generate a distance that's around square root of the number of qubits. And after a while, it was hard to kind of break this square root of barrier. And there was some development which kind of slightly breaks it, which is you have an additional polylog factor. Yeah. So so the idea is that we want D to be as large as possible, and here they're able to improve by a polylog factor. It was until like last year that people was able to have a polynomial improvement, so all the way to a polynomial greater than square root. Over there it was using a similar construction, but a clever idea of a twist. And it turns out using the similar construction, but with a more careful analysis, you can actually do very well. So that means your distance can be nearly linear, only off by a log factor. Yeah. So for LDPC code, we want D to be linear. And here they're already able to achieve N and off by a factor by log. And last year, there was also another paper, which is about balanced product. And what it does is that it summarized many of the previous construction, some less similarities. And so they, at the end, they gave a conjectured construction. Yeah. So I just want to note that later we'll see this balanced product again. Okay, so that's everything about history, and I want to state the main results. So the main result is that we're able to find the quantum LDPC code with linear distance as a constant rate if we have the following object. So if there exists a expander graph with vertex expansion of this number, then we can find quantum LDPC. Okay. So the plan of the talk is that later, we'll go to the more technical part, which is we'll first talk about a graph construction, the left-right KLA graph. Later, we'll use the graph to generate the code, and then at the end, we'll see a bit about like how we prove it. Okay, so first we'll talk about this left-right KLA graph, and before that, we'll review what's a KLA graph. Yeah. So to define a KLA graph, we start with a group, and then we have generators. Oh, we choose a subset of the group as our generator. Okay, and what is KLA graph built on G and A? It will be a bipartite graph. So you have G vertices on the left and G vertices on the right. And the edges are connecting G and AG. So when the elements differ by a factor inside A, then we connect them. So this would define a graph. Similarly, for KGB, we can also do a similar construction, except that now we multiply B on the other side. So we have G to GB.
So A and B are a group outside, I mean, now related to G is by some action you define.
Yeah, there are elements inside G. So A is inside G. So you have and so the multiplication would be the group action.
Okay, I see.
So that's the usual KLA graph. And in fact, so I showed this inside. So I draw A horizontally and the G vertically. Sorry. I draw GA vertically and then GV horizontally. And turns out we can actually piece these two things together. And so we can define something that looks like a 2D object. So again, we pick a group, and then we again pick two sets of generators inside G. And now we'll define a left-right KLA graph. So this graph has vertices there are 4 copies of G. So you have G, 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 and G. Now the edges, there are 4 sets of edges. So they're running horizontally and vertically. So horizontally and vertically. So these blue ones will be the vertical ones. And then at the end, you'll have the squares. So the squares would be something with the 4 vertices on the 4 groups, on the 4, these 4 different blobs of vertices. And so they will have label G, AG, GB, and AGB. So you can actually see one of the squares in this picture. Yeah, okay. So starting from G, using this blue edge, you will connect to AG. And if you go with this red leg, you will go to GB. After that, if you do this red leg on AG and this blue leg on GB, you actually will meet up at another point, which is AGB. So this over here, you kind of see that this A action and this B action, they commute because you can first apply A, then apply B, or you can first apply B and apply A. They will match up. So yeah, and this is actually the nice property that allows us to define the code, which we would do next. Oh, and before that, we'll look at more pictures of this Cayley graph, just to give more intuitions. So this one is the one that we have seen. So that's a picture of a square. And here, since G can, you can apply different kind of A on side G. And so you actually, if you focus on an edge, a red edge, you would actually see like a lot of flaps, like a book. So you have multiple squares coming out of the same edge. And if you focus on a vertex, you would see some structure that looks like this. So you have multiple edges coming out, and then you also have multiple squares. Yeah, and the last one is just a more realistic picture. So you have all these points and all those edges.
So you hope to make A as large as possible and B too?
Okay, so later,
more pages.
Yeah, so later A and B, the size would all be constant. We want them to be constant. And we will try to make G as large as possible. So G would be proportional to the size of the group, be proportional to N.
N is the number of
qubits, yes.
Yeah, okay. Logical qubit.
Yes.
Physical qubit. Oh.
Yeah, so the idea is that there will be a lot of points. Yeah, because the number of points is proportional to the group, so there will be a lot of points. However, locally, if you focus on a vertex, everything is finite. Yeah, because A and B are finite. And so locally, everything is simple, but at the same time, there are a lot of points.
So the G should be correspond to the physical qubit, right? And the square correspond to the logical qubit.
That's what we'll go to next on the next slide. So the next question is, how do you go from graph? So now we have to talk about the graph, but how do you go from graph to the code? So that's what we're going to talk next. Okay, so how do you go from the graph to the code? Okay, so just to remind ourselves, how do we define a code? We need to specify how the Z stabilizer acts on the qubits and also how the X stabilizer acts on the qubits. And yeah, and so how do we read out these data from the graph? Okay, so first, every vertex on the top left, they'll be correspond to a Z stabilizer. and all the vertex on the bottom right, they would correspond to an X stabilizer. And for the rest, they would correspond to qubits. So what that means is that, okay, so say for a particular stabilizer, so that would be a vertex. So we ask, okay, which qubits does this stabilizer act on? Then, okay. Actually, let me first do the graph. So we have this vertex, and we can look at the neighboring vertices. So you have some neighboring vertices going down and some neighboring vertices going sideways. Then the way this stabilizer would act is it will act on these qubits. So they will apply Z on these qubits. And same for the X stabilizer. So for each X stabilizer, you will look at the vertices that it connects to. And those would be the qubits it acts on, the stabilizer acts on.
So it means different qubits, so acting on Z1 and Z2, Z3 corresponding to qubit 1, 2, 3.
Yeah, okay. So yeah, depends on, yeah. So the stabilizer will act on the neighboring qubits. So that specifies HX and HZ. So that tells you how the stabilizer acts. But next we have to make sure that they commute. So how do we make sure that it commutes? So we know that Z stabilizers commutes itself. So we have to check the relation between X and Z. So if an X stabilizer and a Z stabilizer, they act on a common qubits, then what happens is that because of the square, because we know that there is always a square, and so we can find another qubits on the other side. So that means any X stabilizer, given any X stabilizer and Z stabilizer, they would always meet on even number of qubits. And so since even under F2 is equals to 0, so that tells you that the X stabilizer and Z stabilizer commutes inside this code. So that defines the quantum code.
So, like one point in the qubits on the on this graph, is representing like a state in the code space.
Can you read that again?
Like so, like one point in the qubits, like
so one point in this set.
If we are considering like the previous AQB case, so like the point you draw here is a AQB state and is satisfy the like S acting on this state equal to its original state, like is in the code space H.
Yeah, so to define the code space, we need this. We only need to know the stabilizer. Once we have the stabilizer, we know what the code space is.
So like in the so like here only have K state in this like up right corner. Like this is your number of the dimension of the code space. So we only have K in this graph, right? Is that correct?
Okay, let me see. So okay, so your question is how N and K kind of relates. Like how can we see N and K inside this graph?
Yes.
So N over here would be the number of vertices here plus the number of vertices here. So that means n would be equals to 2g. For k, you need to look at how the stabilizers. What I mean is that each stabilizer, it would cancel out a logical qubit. So that means k is roughly equals to the number of qubits minus the number of stabilizers. So in this case, it's if we just take it, okay, this is approximately true. So if you just, what I mean by approximate is that if x stabilizers, they have linear dependence, then you can, then. This equality is only true when all the stabilizers are independent. And if we assume that, then you will see that it will be 2g minus 2g, which looks like 0, which is really bad. But later we'll see a rescue for that.
Okay, so this blue square you draw is like each point is actually many points in the graph. So like this x stabilizer is acting on maybe a qubit here, and only like depending on the which stabilizer, then it only acting some specific qubit. So like this here, like in the upright and the left down corner, there are only like 8 qubits separately, right?
It depends on the size of your group.
Okay. Okay.
Sorry, I am confused.
Yes.
In the square here, all the points, I saw there are different elements in the group, or
yes.
each. So why is 2g? N is 2g. Because the fourth square, all the elements, it should be counted into the g. Are they repeat or not?
So you mean in
I mean, a square have 4 elements in the.
have 4 elements. Yes.
Yeah, and you have only the bottom left and top right corner as the qubits, so it's g over 2 elements.
Okay. So I guess what you're thinking is that the whole thing has size g.
Yes.
Okay. Yeah, but let's see. Okay, so in fact in the construction, I copied the g 4 times. So that means each part has all the elements inside g. So all the elements inside g would appear in one of the corners.
Okay, that makes sense. I see. Thank you.
Yes. Okay, so that's the code. And okay, let's see. Okay, so that's the code. And since we have checked the commutation property, that means it's a quantum code. And now we can actually kind of understand better what the assumption means. So the assumption requires is saying that, oh, we need some kind of expander. And what this expander is referring to is that like this Cayley graph. So if we only take the points on the top left and the points on the bottom left, and we look at its edges, then this defines a graph. So we want this graph to be expander, and also this graph to be an expander. If these two graphs are both expander, then the claim is that, okay, as a whole, like this qubit construction would be a like a good LDPC code. Or let's say it has large distance. So that's just
sorry, when you mention distance, you mean the distance between any 2 qubits here, including within each corner and at different corner, their distance is large enough?
So distance here is not the distance on the graph. It's a distance on the code. So that would be like that would be this definition. So you look at the logical operators.
Then in the graph, how can you find the error? I mean the distance we
Logical
define here.
operators. Yeah. Yes, it's not easy to find. So what you're talking about is, okay, how do you do the error? Like, how do you do the analysis on showing the distance is large? And that will be covered later. Yeah. Okay. So, yeah. So let me say a few more things. So we have these expander graph, and it's probably the time to say more about this expander graph. So what's the more explicitly, what do we want? So what we want is okay, so we call it bipartite graph to have alpha, beta, left to right, small set expansion. If for any set S on the left, which has small number of vertices, so then the neighbor of this set on the right gives you a beta expansion. So now we can go back and say what we need. So what we need a bipartite graph with expansion in both directions, where the beta has to be larger than this quantity, and W is the number of edges going out from a vertex. That's the degree of the vertex. So W is the degree of the vertex. Yeah. For now, let's assume all the vertex has the same degree. So that's what we need. Yeah. Okay. So yeah. So now we can look at the full main result, and and that's like everything we want. Yeah, I have explained. So the main upshot of this is that what we are able to show is that, okay, this expander is a 1D structure, and this quantum LDPC code is a 2D structure. So this result is saying that if you have a nice structure in 1D, oftentimes you can extend it into a nice structure in 2D. So in this case, it will be that if your graph has nice vertex expansion, then your 2D code has linear distance. So this could be a more general phenomenon, and yeah. Okay, but for now, we'll come back and say a few more words about the proof. And before that, let me address a thing, which is, in fact, the code I mentioned is a simplification. That's not exactly the code we are working with. The reason is because of someone mentioned. So someone mentioned that, okay, if you look at K, you actually found that a naive calculation shows that it's 0, which seems really bad because we actually want it to be linear to G. So the way to solve that is we can actually do a lift to this basic code. That means you can actually, so here it's G. They're only the vertices are labeled by G, but actually you can make more copies of it. So for example, you can turn into a 2 times 2 that many points. And so on. So you can actually do some kind of lift to change the number of vertices. So in this example, say these two are qubits, and say these two are qubits, and say these two are stabilizers. Then now, using this naive computation, it will be 4 plus 9 qubits minus 6 plus 6 constraints. or stabilizers, 6+6 constraints. And so overall, you found that it's equals to G, and which is proportional to the, which is G. And we can show that it's actually proportional to N, because N is the number of qubits. In this case, it's 13G. So you can show that, in fact, you can achieve finite constant rate in this case by taking a lift. And previously I mentioned this balance product. So it turns out if you look more closely, you will find that the construction I provide here with the lift is equivalent to their construction. Yeah, that's a fun fact. Okay, so that's what so we defined the graph and also talk about how you construct the code. And so now I will give you a taste of the proof.
So sorry, before you going on,
yes.
Can you explain? Is the square that you draw like 2 times 2 or 2 times 3 or 3 times 3? Are they just repeat? I mean, copy of the element in G?
Yes, pretty similar. Pretty similar. So if you want to know more detail, the detail would be that. So between each pair on the top and bottom, you'll construct a different A. So that means, say this is labeled by 0, 1 and this is labeled by 0, 1, 2, then you would choose not only one A, but you will choose 6 different A's, which is 6 different generating sets. So A00, A01, A02, A1. Yeah, let me group them more nicely. So you have a generating set for all of these, and so that would, Then for each pair, you will have some edge connecting them. Then you can copy it on the side. So what I mean is that all the vertical edges will be the same between each column, and all the horizontal edges will be the same in each row.
So it means you have different group. I mean, different sets of the A and B.
Yes, same group but different generators.
And A and B, are they necessary to be a subgroup, or they are just sets?
Subsets, yes.
Okay.
Yeah, they only need to be subsets of G.
I see.
Okay, so that's the code, and we'll just say a few words about the proof. Yeah, so first thing is we have to remind ourselves like what's the actual thing we want to prove. So using this, this is where this language become handy. And okay, so over here I show the complex. I show the chain complex, and over here I show the definition of the distance. Then we can like read it out. Then it will be that. So this condition means, okay, if you have a logical operator, which if you have an operator which is logical, so that's this condition, and then it is not trivial, which is this condition, then this logical operator has to be long. So this is what it says. Equivalently, it means that, equivalently we can like swap the conditions around, and we can, and the new goal would be that for any operator that is a logical operator, and if the operator is short, then it has to be trivial. So that's the equivalent goal, and this is what we'll show. So what we'll show is that if V0 satisfies these conditions, then we'll try to find a V-1. Okay, so the next question is how do we find it? So the way we'll find it is we'll apply a algorithm that was known inside the classical world. So in the classical coding theory, you have these expander codes, and there's a decoding algorithm which works the following. So let's see. Okay, yeah. So what it'll do is it will try to change a bit on v -1. It will try to change a bit. And we'll see if the size of v decreases, size of v0 decreases. If it does, then we'll flip it. We'll change the bit. And if not, we will just then we'll just look at the next bit. So yeah. So how the algorithm would run is that the v1 with v0, it will have a shorter, the Hamming distance will be shorter and shorter until at some point which there is no bit on v -1 which we can flip. So at that point we are stuck. And so the question is, like, when is the stopping point? Ideally, we want to stop it at v0 equals 0, because in that case, that means we found a v -1, which when we apply the partial, it becomes v0. Yeah. So what I mean is that now the new goal is to make sure that the algorithm always succeed, in the sense that it's the point that it is stuck, it's only at the case where v0 is already empty. And that means there's nothing more to decrease. Okay, and now we'll go back to the square graph. So this non-stopping condition, we can translate into some property of the graph. And what we are able to show is that if the 1D graphs are good, I mean, they're good expanders, then you can show that, okay, this property of the graph always satisfy, and so the algorithm always succeed. So that means we found v -1. So that's the idea of the proof. And so just to finish, so the main result is that if there exists some nice expander graphs with large vertex expansion and also have a group symmetry, then we can find quantum LDPC code with linear distance and constant rate. And the way we show that is that we first construct the left-right Cayley graph. Then we use the graph to construct the code. To prove that this code has large distance, we use greedy flipping algorithm. And then we need to show that the greedy flipping algorithm always works. So we need, and here we need a large vertex expansion to make sure this happens. Yeah. And okay, and so what's next? So one thing is that could there be other applications to the square graph? So it turns out recently there's in the classical world, in the classical error correcting world, there's a question which is called the local testable code. So people want to find some local testable code with with some nice properties. And they also somehow found the same construction, which is the square graph. And so maybe the square graph has some pretty nice properties that could have other usage in other places. The second question is, could there be higher dimensional generalizations to this? So here we're doing like 1D and 2D, but maybe you could also construct some 3D versions or higher dimensional versions. It's not clear how to do this, but it could be possible. Next very interesting thing is that how are these results related to quantum PCP? However, it may be too early to talk about this because we still have the most important question, which is we want to close this loophole, which is that we want to solve the classical problem, 1D problem, which is we want to find the lossless expander with symmetry. Yeah, so that's everything. So I can take some questions.
Okay, thank you for the very nice talk. Is there any question or comment from the audience? So in your main proof, can you remind us the law of mu0 and mu-1 and the partial operation? So I do not get physical intuition about this.
Yeah. So I guess I would say that this is the reason that people like these partial language is mostly because now you can bring in many mathematical tools inside. And that's the only purpose, like that's probably the main purpose why people like this language of using chain complexes. Yeah, but there aren't anything physical about that.
Yeah, so the mu nu0 and nu-1 are they corresponding to some matrix you want in the error correction you want to find, or is the partial?
V0 correspond to like some vectors inside V qubit, so that correspond to some poly string. So this partial operation is checking that it commutes with the X stabilizer. So partial, so V0 is the poly string, some poly string, and this partial 0, this checking this result is to make sure that this string commutes with all X stabilizer.
And mu-1 is before the poly string or after?
Yeah, so mu-1, it's it would correspond to I generate. Yeah, it's corresponds to the generating set of the Z stabilizer. So that means I'm trying to construct the trivial logical operators. So this is what I mean. So if I take V-1 inside this vector space, if I take all of them, I apply this partial, then this thing I end up with is the trivial logical operator. It's the same set. So that's why I don't want my V0 to be inside it.
So is there any connection for this to the graph like G and AB to define before?
Yes, good. So exactly. So that step would happen here inside. So we have to translate all those conditions, these partial objects, back into some property in the graph. And this partial object is basically telling you something about the edges. And so that's kind of the relation. So for example, if you have a node, a point inside the Z stabilizer, so that means say the vertex is I, then that means your vector at the ith position equals 1. And all the other positions are equals to 0. And so you can consider that vector, and then you apply partial on it. You will find that it's exactly the random walk over that point. So it's all the neighbors of that point. So that may be one interpretation. So you can translate all these partial. Yeah, that's one example of translating these partial into graph properties.
When you say the new I equal to 1 and all other I bar equal to 0, are you referring to all the group elements within one corner? Starting from one?
Yes, that's right.
Okay.
So actually, maybe G is a better notation.
So you are trying to make a larger distance for each element in a corner, and then to see if they're connected to other qubits. Are they separable from larger distance defined in this kind of chain property?
Can you repeat that again?
I mean, you are trying to see if all the elements in the group are separable from other neighbors, and then you use this kind of chain property to show expand the graph by this partial operation. You see, you are trying to say that they are separable. I mean,
or let me give an example. So where does this losslessness comes in? So one example is that, okay, I have some points over here. I have some points on this top left corner. If the thing is lossless, that means after applying partial, how do I say this? Yeah, okay, this is what I want to say. So if the graph is lossless, here's one implication, which is partial v0, the size of partial negative one actually. It will be kind of, there will be something like that. So recall that lossless is saying that there is a lot of neighboring edges, and so neighboring vertices, and so losslessness would imply something like that. So that means after applying partial, your Hamming distance is large.
I see. So it means after the partial operation, you at least preserve some qubits. That's still distinguishable, larger than some beta v something. Roughly speaking, is that the case?
Sorry, I'm not sure.
Okay.
Yeah.
Okay. Okay. Good. So any other question or comment? Okay. If not, let's thanks Debbie again for the very nice talk. Okay. Thank you.
Yeah. Thank you.